Good morning. I will I will wake you up with a little bit of hydrodynamics. I always start out with this slide just to show what a hull vane looks like, because most people haven't seen it. It looks basically like a hydrofoil, but unlike a hydrofoil, the idea is not to lift the entire ship out of the water and ride on the foil, but the idea is to generate a beneficial force and to reduce the stern wave of the ship basically, and therefore the wave making resistance of the ship. I'll give a little bit of history, then show how it works, and then show some examples of installations that we've done. It was invented by Pieter van Ossanen. It's a Dutch hydrodynamicist. He worked for 20 years at the Marin Research Institute, and then in '92 he set up his own company. And he was involved with several America's Cup campaigns, amongst others in '83, where he helped Team Australia win the cup by adding winglets to the keel, so they could get more lift out of a limited drag. As you still see some sailing boats with wings on the keel. And then in '92, in a second America's Cup campaign, they had some spare time in the towing tank, so they experimented with winglets on the rudder. And they noticed that it gave a propulsive force. So he started thinking, like, where does this come from? And they found out the mechanics of it. And this is actually an evolution from that. In his own company, in '96, he was asked to optimize a catamaran, which is sailing in the port of Rotterdam, a 30-meter vessel. And there he devised basically what we now call a hull vane. It wasn't called a hull vane then, but it's the same. It's a hydrofoil, but between the hulls. Saving quite a bit of resistance and increasing the top speed of the vessel. Then in 2003, a third America's Cup campaign, they actually built a full-scale, they did model tests and a full-scale hull vane on Defi Areva, a sailing yacht. You can see on the picture, maybe if it's not too small, the tip sticking out of the water. Performance was good. They had about 8% reduction of resistance at 10 knots under the heel sailing. The problem was that due to the rules, they could only fix something on the center line, and that was too weak with the center line strut, and it actually broke off before they used it in the races. Then they shifted focus to commercial ships. We did some studies on dredger and container vessel. I'll show a slide about that later on. And then his company was quite early in investing in CFD, computational fluid dynamics software, which you can call like a dry towing tank, numerical towing tank. And this really helped in the development of the hull vane as well, because you can see what the effect really is, how the flow is not just on your surface, but a meter away from it. And you get all the forces from it. And you can do a lot more iterations at a lower cost than you would in a towing tank. This led to 2 vessels being launched with the hull vane last year. One is a 55-meter fast supply vessel, and one is a 42-meter motor yacht. How it works, basically, there are 4 effects. The first one, I usually make the comparison with an airplane wing. We all know, suppose this is an airplane wing in a horizontal flow. It gives a lift vertically up, and your engines give the forward power. If you take that picture and you tilt it 10 degrees forward, you have basically what you have under the aft ship. The flow is not horizontal, but going upwards, and the lift generated is not vertically up, but angled forward. So that looks like this. It's angled forward, which means it has a vertical component, but also a horizontal component, pushing the vessel forwards. Then there's a second effect. With any wing, basically, you accelerate the flow on the top, so you create an area of lower pressure, and that is an area where you usually have a higher pressure, and that you can see in the stern wave, which is basically a visual representation of the higher pressure. So what it does is it reduces the pressure wave caused by the ship, and this is the wave profile for the 55-meter boat, doing 20 knots on the upper side without hull vane, the lower side with hull vane. And as a general rule, you can say that when a ship produces less waves, it will also consume less energy. That's also why you have the bulbous bow in the front very often at ships with a certain speed range. And this is basically the similar effect, but at the stern. People call it sometimes the bulbous bow of the stern, although it looks totally different. But then the third effect is vertical force. It gives a trim correction, like there are other systems like interceptors. On large vessels they will use ballasting just to bring the bow down. But most vessels, when they go fast, they have a tendency to ride with the bow up. And this helps avoid that and keep it more at an even keel, which is hydrodynamically more efficient, at least if you don't want to go into planing mode. And then the fourth effect is when you are sailing in waves, the hull vane will actually dampen the pitching motions. And pitching causes a lot of added resistance, and we take away a bit of the added resistance. And this is a part that in some sectors they are actually more interested in than the fuel saving aspect. For example, naval vessels, because they want a stable platform, or offshore they want to increase the operability. Now, what we've done, suitable ships, on ships which it can be applied, we look always at the Froude number, which is the speed to length ratio, and that should be around between 0.2, 0.7. In some cases can be higher and lower, but as a general rule, and for the ship lengths, you can see what that means as a minimum and maximum speed, and that's quite a wide range. So suitable ships are offshore supply vessels, specifically fast offshore supply vessels, like the one on the top left, where it's installed, motor yachts, then ferries and ro-ro vessels, or car carriers as well, and then naval vessels and Coast Guard vessels. We get the most success on the right. On the left, it depends a little bit of how the hull shape is, and because many of the new ferries, they have a very hollow aft body with a very horizontal flow, and then we don't get good performance. But in some ages, the hull shapes were different, with buttocks really running upwards towards the stern, and then we get generally good performance. We have now 3 full-scale applications. One is the fast supply intervention vessel, which I'll come back to. One is the motor yacht. Here you see how it's integrated in the stern. Because of this, we couldn't do sea trials without it, and the number is basically based on CFD, comparing the hull with and without. But for both of these ships, I can tell you that even without the hull vane, they are very fuel-efficient vessels. They're new designs and really up-to-date. So we're not benchmarking against some older, outdated design. And then there is the catamaran. There you could have the discussion whether it's a fix for a bad vessel. It was a little bit heavy on the build, and the hull vane is basically between the hulls to correct the trim, but also it gives a forward thrust force. These numbers are from the model tests, the 8 to 20%. The Carina was in July last year. Basically, the builder had read about the hull vane and they wanted to try it. So they built it, we designed it, they built it, and they did sea trials first day without and the next day with the hull vane. And these were the results that we got. They were independently monitored by Belconet, which is a company doing all the speed trials in Holland. And you see that the savings went from 10% propulsion power all the way up to 15% at maximum speed. So very good savings, actually, on a vessel type where it's difficult to get these kinds of savings. There is not much available for fast vessels. We did also a study in CFD for the seakeeping at the request of the client, because they have the accommodation in the front and they also wanted to know what happens on the aft deck. So we studied one wave condition and saw that the vertical accelerations were reduced by 20% in the aft ship, 7% in the middle, that's damping of the heaving basically, and 10% in the foreship. Also the added resistance reduced by about almost 30%. So it's very efficient. Then for P&O ferries, last year, this spring, I believe, we did a study on Norbank and Norbay. There are 2 ferries sailing between the UK and Ireland, up and down all day. Lower savings percentage, 6% at 20 knots, which is their normal trading speed. But these vessels have so much power that with 6% savings on a yearly basis are enormous. And the payback period becomes really short, a little over 1 year only. Yeah. I know that one came in. So there are cost-saving advantages. Of course, you save fuel, so that's operating expenses. But also, when it's a new building, you can get a higher performance and better savings. And more savings because you can reduce the installed power needed to get to a certain speed. And that doesn't inflict on your safety margin because you just reduce the resistance of the vessel basically. And on larger vessels with kilowatts installed for more than 3,000 kilowatt, this will often already pay for the hull vane. So in the build phase, you can actually build the vessel for the same cost, but it will have less fuel consumption in the life and a longer range. Then the pitching, this is from a study that we recently did on a Dutch patrol vessel, the Holland class, with similar results. I think we got 13% reduction of the vertical accelerations on the helicopter deck, which is what they were most interested in. But it's also, of course, comfort on board, more safety for your cargo, and a more stable platform for naval systems, for example. Then from the yacht, we also know that it reduces the roll. This is more on the smaller vessels and less on the big vessels, but that's because the tips of the hull vane basically, they have a lot of added mass in the water that they move when it rolls. And we see that it both reduces the amplitude, so the maximum angle of roll, but it also increases the natural roll period. So the vessel will roll slower, and that is more comfortable and easier to eliminate with stabilizers. And then on this vessel, we also did zigzag tests. I don't know if you can see it, but on the left is without hull vane. We had an overshoot of about 3-4 degrees, and that went back to 2 to 1 degree. So the vessel has improved controllability, which is actually probably because of the vertical struts adding to the directional stability, but without a resistance penalty like you would have with coarse fins, for example. And then you have a reduced stern wave. This is from the same vessel, the 55 meter, without hull vane and with hull vane, which can be important for inland ferries, for example, if they have a low wake restriction, or patrol vessels wanting to launch a smaller rib from a stern slipway, for example. How we go about it is rather complicated because we never know in advance, because of this first and second effect, whether it will work on a ship and what will be the savings percentage. So we always start out with what we call a feasibility study. For one speed or several speeds, we see what is the performance, and then the client, based on that, they can make their calculations before we start further engineering. If they decide to go ahead with it, we build it and we design it and build it and can supply it to the yard. This first part, the hull vane study, we do that generally on a no cure, no pay basis. So we will give the client a minimum percentage in advance that we will achieve. If we don't get that, 5% for example, then the study will be free. If it's more than that, the study will be paid, but that already amounts to the purchase price basically of the hull vane. So there's no risk for ship owners to have the study done. So concluding, I don't know if I'm still in the time. It's a patented technology, reduced operating costs, reduced capital expenses. A wider operational profile is very important for offshore vessels. We were in the towing tank last week on a offshore crew transfer vessel, quite a slower ship. But they're looking mainly at it to broaden their working days, to have more working days in the year and have safer operations, putting boats over the side and stuff like that. Safer deck operations and more comfort. And then for ship owners or shipyards, I think this is a dream because it's innovative still, but they don't have to invest in R&D. We've done that in the past 12 years. And because we know all the forces from the CFD, we can design it with no vibrations, no fatigue issues. There's also no class-related issues because it's outside of the hull. Only thing class wants to see is drawing showing the reinforcements in the stern, so that we don't damage the stern with our lifting force. So that's, I think, that the main thing is that you now know what it is, and if in a couple of years you will see more of them, like you now see the bulbous bow, you will know what it is for. So I thank you.